Okay, I can start with the brief introduction, Zeynep. Thanks, first of all, for being with us today. And I will introduce you. Zeynep received her BA and MA degree from Koç University. And for her master work, she was in the track of developmental psychology and work on the effects of intrusive parenting on children's cognitive development. And it is a TEÇKE project, am I right?
Yes.
So TEÇKE is a very big nationally representative data, and she worked on that data. And after her graduation from Koç, she did not directly jump into a PhD program. Rather, she worked for 2 years as a school psychologist in Istanbul, and I remember those days. And after that 2 years, she applied for some programs in Scotland, and then you did your PhD in evolutionary and comparative psychology, right?
Yes, yeah.
And work with the chimpanzees.
Yeah.
This is something very new for us, and I hope we will hear some exciting studies from your PhD today. And currently, Zeynep is a postdoc in the same university and working on the executive function battery for 3 to 5-year-old children. Probably you had a problem due to the outbreak pandemic.
Yes, just at the end of data collection. Yeah, right.
Yeah. Okay. Thanks a lot again, Zeynep. It's my pleasure to introduce you. And yes, floor is yours.
Thank you. Well, thank you very much for inviting me and this introduction and everyone joining today in their last week. I'm presenting, this is the first time I'm presenting my research back home in Turkey, so it's really exciting for me. It's a great opportunity, and I also hope you enjoy and find the studies interesting. There are 2 studies I will talk about today where we explored the developmental and evolutionary origins of inferring unseen causes. But before talking about the empirical work, I will start with talking about causality and the challenges of studying it in young children and also non-human animals. After I present the first study, I will take a little break for your questions, and if you need, you can just look away from the screen for a bit. And then I will move on to the next one and conclude. Okay, so let's start. Imagine a scientist presented with a new disease, a woman hearing a loud sound coming from outside, a child discovering their candy bag open and candy spread on the floor, and a chimpanzee coming across big footprints on the forest floor. They all face a similar challenge. There's some information readily available to them, that is the disease, the sound, the candy bag, and the footprints, but there is also a gap in their knowledge. They do not have direct evidence about what caused these events. And making inferences about unseen causes to detecting this culprit in all of these cases is critical for several reasons. It allows us to make sense of the environment. For instance, you may want to know if the sound is the sound of an explosion or thunder. It helps us to predict and prepare for the future. As a chimpanzee, if you see the leopard footprints, you may want to climb really high up on the tree. It allows us to manipulate events for better outcomes. For instance, if you know it's the dog who got your candy bag, you can put it in a drawer next time. And it also allows us to prevent events from happening altogether so we can avoid unwanted consequences. As a scientist, you can develop a vaccine to fight the unseen virus. Given the importance of this ability, the question is, will the scientist, the adult, the child, and the chimpanzee be able to infer what caused these events? While there is no doubt that the scientist and the average human adult look for and they detect causes, given such incomplete evidence, there is less consensus on when this ability emerges in human development and whether or not this is a uniquely human ability. These are the two questions I will be basing my talk on today. So is this something we are born with? Do we look for causes even very early in life? And do we have this capacity perhaps present in birth? Or is it something we acquire over time, perhaps with the development of language and the more we learn about the causal relations in the world via teaching? The developmental origins is important because if this is an ability that we are born with, it's also possible that we share it with our closest relatives. But whether or not this skill exists at all in non-human primates is a matter of a huge debate. And these issues mainly originate from the fact that making inferences about unseen causes is not the only way of responding appropriately and effectively in the face of such incomplete information. There are other simpler and cognitively less taxing routes to deal with the incomplete information. Before we go on to these alternative routes, let us talk about what it means to engage in causal reasoning and inference making. And I will use this causal reasoning and inference making interchangeably because in the context of my research, they basically mean the same thing. Causal reasoning is defined as the act or process of reaching a conclusion about something from known facts or evidence. If we go back to the examples that we talked about in the first slide, it will be going backwards from the evidence we see to reach the causes. And this may be very straightforward and very simple for human adults like yourselves, but it's actually based on an extraordinary capacity. At the heart of causal reasoning is the ability to represent abstract structural information beyond concrete perceptual information. Let's give an example to what these concrete and abstract information mean. Imagine you observe the wind blowing and the fruits fall from a tree. The concrete perceptual information here would be the branch laden with fruits. They lead to a desirable outcome when the wind blows. So exactly what you observe is what you get in this context. However, there is more to be gained here than that is directly available in the environment. That is, the objects, in this case, the branch, the fruits, and the wind, they interact in a certain way with one another. There is continuity and connectedness between the branch and the fruits, and this connection is broken by the strong wind. If you can represent this abstract causal relationship about how events and objects interact with one another, you can flexibly generalize this to novel problems that share no similarity to this problem. For instance, in the absence of the wind, if your football gets stuck in the branches, you can shake the branches to get it. Hence, you can exploit the same relationship with only one observation. And when this capacity for abstraction is coupled with our existing knowledge and also the knowledge of scientific method, as humans, we are at our most intelligent. We can learn about cognition, cognitive processes from behavior. We can design technologies to fight unseen viruses. We even discover the structure of the solar system based on the movements of the planets. So to reason from evidence to detect unseen causes is an extraordinary capacity. But, like I mentioned earlier, there are alternative routes to dealing with incomplete information. You do not always need to reason about causal relationships when you have some evidence in the environment. Another way is to learn by association. The good thing about causal relations is that the events that are causally related to one another tend to co-occur. So if you encounter certain events repeatedly in close spatio-temporal proximity, you may predict one from the other without any reasoning involved, even in the absence of any explicit awareness. For instance, if you've seen a leopard passing by and leaving footprints behind 20 times before, the next time you see the footprints, you can successfully predict the presence of a leopard. And such associative learning is common to humans, even to infants, as well as to many of the non-human animal species. Another way that is unique to humans is culture. Your culture prepares you for causally relevant stimuli through testimony and explicit teaching. The child with the candy bag in our example, for instance, may learn that the dog is to blame for the open candy bag because their parents told them so, in the absence of any reasoning by themselves. And indeed, once we have language, we learn a great deal about unseen causes that we would possibly not be able to extract by ourselves. For instance, we know that the Earth revolves around the sun, but I guess no one came up with it themselves. We learned it from others. But also think about how common it is in a young child's life to hear about such unseen causal relationships. We say things like, he cries because he's sad. It doesn't work because it's not plugged in or there are no batteries inside. We say, don't touch it, it will burn you because it's hot. So once children have language, they're provided with information directly without any reasoning by themselves. So from a comparative and a developmental perspective, one challenge has been to distinguish the causal reasoning route to associative route. How do we know when an animal or a child solves a problem that they didn't solve it based on their past learning with that object or event, but they reasoned about it? And from a developmental perspective alone, it's also been a challenge to distinguish causal reasoning from cultural learning. How do we know that children were not told about this information, but they detected it themselves? So let's start with developmental research. To overcome the problem that children may successfully solve causal problems based on past experience and associative learning, children were presented with completely novel relationships that they have never seen before. And one of the most influential and commonly used paradigm is the Blicket detector, developed by Alison Gopnik and colleagues. And you may know Blicket detector very well, but to briefly explain, it's a machine, it's a made-up machine. Blicket doesn't mean anything in real life, but this is the machine that lights up and plays music when certain objects, but not others, are placed on it. And children's goal is to figure out which objects light up the machine, which are the Blickets and which are not. For instance, in this classic study, in both conditions, children observe the same contingencies, the same associations. The Blicket detector activates 3 times when the cube is on it, and it activates twice when the cylinder is on it. But children as young as 2 years of age, they do not simply rely on this associative information when they detect Blickets. They say only the cube is the Blicket in the first case, in the top condition, because the cylinder activates the machine only when it's together with the cube on the machine. In the second case, they say both objects are Blickets. So the researchers argue that children are able to extract this abstract information based on the dependencies between objects, and they draw causal conclusions from the patterns they see in the world, just like adults do. And they have this theory-like causal reasoning ability. However, there's one thing that complicates the matters. There's one issue here. When you present children with arbitrary events that they have never seen before, like the Blicket detector, you need to explain it to them so that they can solve a problem. In this example, the experimenter would say, Blickets make the machine go, or in other studies, there are other similar explanations, such as, what did I use to make this like this? Which blower made the candle go? Is it X, Y, or is it something else? So with these questions and instructions, the experimenters are giving the causal structure verbally. Further research has found that such instructions and also prompts about potential unseen causes, as in the something else example, had an impact on children's propensity to solve these problems. In the absence of this verbal scaffolding, the 3-year-olds and some of the 4-year-olds failed to solve the same problem. For instance, when the experimenters just said, watch, look, oh, look what happened, kind of things. Therefore, although Blicket detector studies are a great way to distinguish associative learning from causal reasoning, if we want to see whether children can infer causality from evidence alone, we need to remove this verbal scaffolding from the task. So we need to come up with tasks that do not need verbal explanations. The benefit of a nonverbal task is that it will also allow us to make direct comparisons between children and non-human primates to examine the evolutionary origins. In my PhD, I worked with chimpanzees and capuchin monkeys. We share a common ancestor with chimpanzees 6 million years ago and with capuchins 35 million years ago. Chimpanzees live in Africa and the capuchins live in South America and Central America. And both of these species are commonly used as non-human primate models of human causal cognition. They are large-brained compared to their body size, and they stand out amongst primates, especially with how they deal with their physical environment. Their diets rely on seasonal resources, such as fruits. So when the fruits are scarce, as in the dry season, they need to extract food from inside tree barks, husks, and shells, and underground nests. Chimpanzees engage in stone tool use to crack open hard-shell nuts, fruits, and invertebrates. They do engage in ant dipping, fishing for termites and honey, and sponging up liquids. Capuchins, these are the capuchins, are also really good at accessing these foods by pounding, banging, and smashing them with hard objects, as well as sometimes using probing tools. But these are very costly activities in terms of energy, and animals should engage in them only when it's highly likely that they will get a return. If the nut is not full, but it's empty, there is no reason to just spend so much time with the rock to break it. Therefore, the ability to detect hidden causes or events based on incomplete information would largely benefit these species while they deal with the physical challenges of their lives. And such tool use behaviors are underpinned by understanding causal relations, representing goals, planning complex action sequences in humans, but whether or not chimpanzees and capuchins rely on similar causal processes is a controversial issue in comparative psychology. Some researchers argue that causal reasoning is a uniquely human ability, and other primates either learn by association and they rely on generalizations based on surface features of objects like the perceptual concrete information. And limitations in performance in some tasks designed to probe these abilities, causal reasoning abilities, seem to support this interpretation. In contrast, the inferential account researchers argue that non-human great apes can make use of causal information from events happening around them if the situation does not overload other cognitive resources. For instance, the chimpanzees fail a task where they have to use a tool to extract a reward in the face of some traps, but when they are allowed to use their fingers, they perform successfully because using a tool potentially uses up more cognitive resources. But how do we resolve this issue decisively, whether the associative account or the inferential account explains animal intelligence or animal problem solving better? One of the most promising ways has been to compare problem solving using the same surface features embedded either in a causal or an arbitrary context. So in both contexts, animals see the same associations, but there's either a causal relationship or not. If animals solve problems in the causal context, but fail in the arbitrary context, we can say that there's evidence that they are engaging in reasoning beyond associative learning. And here are some examples. In the causal context, the one famous example is the shaken boxes study by Joseph Cole. In this study, the experimenter hides a food reward in one of the boxes and then shakes the boxes one by one. And the one that has the reward rattles and makes a sound, and the other one is silent. In this case, when the food is the cause of the sound, the apes and the capuchins were able to identify its correct location. In a control condition, what they do is, instead of shaking the boxes, the experimenter hides the reward and placed the recorded sound over the baited cup, the recorded sound of the shaking box, basically, and silence over the other one. When the sound only co-varies with the food, but the relationship is arbitrary in this context, the apes and the capuchins cannot solve the problem anymore. Another example is a balance beam study. In this case, there is a balance beam with cups on both ends, and the experimenter extends his arms and releases a food reward in one of the cups, and that side goes down with the weight of the food. While apes can solve this task successfully, they do not choose the lowered cup in a similar arbitrary condition where the experimenter pushes down one side after a few seconds of releasing the food, suggesting that they can distinguish the real physical relationship from the experimenter's own intervention. However, they fail this one, so there are some criticisms to these studies. And these mostly concern that the causal and the arbitrary conditions are not comparable. For instance, Penn and Povinelli claim that in the shaken boxes task, the recorded sound in the arbitrary context is not identical to the actual sound the food would make. That's why they fail in the arbitrary context, they say. And they also claim that the apes can be still solving the causal condition based on associative learning if they're associating the sound plus the shaking motion in the causal condition. And because the shaking motion is absent in the arbitrary condition, they failed. So for the balance beam, they say the apes normally have a preference for immediate downward motion after the food's release because they have learned that by the weights of objects, things would go down. But because in the arbitrary condition, the experimenter lowered one of the cups after a few seconds rather than instantly, that experience of lateness basically weakened the association and hence they failed. So they're explaining the same successes in the causal condition and failures in the arbitrary condition from an associative perspective. Given these criticisms, it is important to come up with tasks where the perceptual features of the causal and the arbitrary conditions should be comparable. They should exactly be the same. And the task should not be solved based on associative learning, or also in the case of children, based on verbal instructions, verbal scaffolding. Given these challenges, our aim was to come up with nonverbal natural causation tasks for testing children and comparing them to other primates. The first study, we called it the Bing machine. We explored whether our participants could use auditory information, auditory cues, to detect unseen causes, as in the first example, when the woman hears a loud sound, can they detect where it's coming from? And I worked with my supervisor, Amanda Seed, and Joseph Cole on this research. So in this study, we presented children with an event sequence where I drop a ball into this apparatus, and the ball contains a sticker inside it. I drop the ball, and then they hear a ding sound as it hits one of the boxes at the bottom. And imagine they choose the yellow box, and the ball is in that one. In the next trial, I drop the ball again. This time they hear a clack sound when the ball hits the bottom, and they choose the gray box and find the ball there. So the illusion here we wanted to create is that the boxes at the bottom are made of different materials, hence they cause different sounds when the ball hit them. So after a couple of trials, you learn that, okay, the yellow box is probably metal, it makes the ding sound, and the gray box is wood or plastic, and it makes the clack sound. But obviously, you don't have to imagine these like causal structure, the different materials. You can only solve this task by learning an association. You can say ding means yellow, clack means gray. So to distinguish these two possibilities, we gave another group of children the arbitrary condition. In this case, you first hear the sound, ding, and then I drop the ball, and the sound is still predictive of the location of the ball. So ding again means yellow, clack means gray, but this time the ball cannot be causing the sounds anymore because it's dropped after you hear the sound. So we have the same associations between the sound and the size, and there's a causal context in the causal condition, and there's no causal context in the arbitrary condition. We hypothesize that if children and chimpanzees have a causal understanding, they will do better in the first condition and worse in the arbitrary condition. I tested 129 3 to 6-year-old children and 11 chimpanzees, and here's what we found. So I'll first describe the features of the graph. At the x-axis, you can see age in months from 36 to 84 to 3 to 6 years. The y-axis is the mean correct responses in 20 trials overall. The red dashed line is the chance level performance. This is where you would perform if you're doing randomly. And the gray area is the confidence interval for the model's predictions. And as you can see, there's a complete overlap between the chance level and the confidence interval for 3-year-olds, meaning that they performed randomly and they had no understanding of the task. But we found that by 4 years of age, children performed significantly better than chance in the causal condition. When we look at the arbitrary condition, when there was no plausible causal explanation, all age groups were at chance level, except for 6-year-olds here. Doesn't look like it, but they're above chance here. At the end of the task, we also asked children how they found the ball, and we categorized their explanations as they have no idea. They said, I'm just guessing, I don't know. The wrong idea, and this was things like, I'm seeing through the box, I have special vision, and also the correct explanations. That would be the boxes made different sounds, or this made a spoon sound, kinds of things. In these graphs, the correct explanations are coded in red. So if you see, there are 2 points in the arbitrary condition, only 2 children, older children, who were able to give the correct explanation, as opposed to many other kids in the causal condition here. And those children who gave the correct explanation in the causal condition also outperformed their peers who gave other explanations, meaning that they were able to solve the problem because they understood the underlying causal relationship. Next, we conducted a follow-up study where we simplified the task by removing the imagination requirement to see if it would improve performance, mainly for 3-year-olds because they were at chance level, but also for older kids. So even though they were significantly different from chance, their performance was nowhere near ceiling. It was a difficult task for them. In this simplified task, I hit the ball in a metal or a wood cup behind the barrier, and you can and shook both cups. So you either heard the ding, ding, ding or the clack, clack, clack sound. And then when I removed the barrier, I asked children to find the ball. They all had the instruction that if you can find the ball, you can get the sticker. But we had a manipulation. In one group, after I hid and shook the boxes, I asked them, which box do you think is in? Meaning the ball. And for the other group, I gave away the hidden causal information that I was shaking and making the sounds by asking, which box did I shake? So this was a much easier task. You can see by 4 years of age, children and 5-year-olds, they're almost coming to the ceiling. They perform well above chance levels compared to the Bing machine. But if you look at 3-year-olds, there's this overlap again. They performed at chance when they were asked, which box do you think it's in? So we did the same study, exact same study with the which box did I shake question, only with 3-year-olds. And this is what we found. Now they are performing significantly above chance. And here you can see the comparisons of 3-year-olds in 2 different question conditions. This was the most surprising finding for me personally from my PhD, because even though I read about this before, that causal questions and instructions help children. I genuinely didn't expect that if you gave the same task, they would fail one and pass the other one just based on the question I asked. And also the red point again are the children who gave correct explanations. There's only one 3-year-old here as opposed to, I think, 6 of them on this condition. But 3-year-olds are not very good at responding to explanation questions in tasks. So that is there still. I also tested 11 chimpanzees in Leipzig Zoo, Germany, with the same setup. So they started with the yellow boxes, being machines causal condition, but they got side biased very quickly, as in always choosing the yellow or the gray box, which implies that they didn't understand the task. And at the right, you can see their performance across 10 sessions, where they get 10 trials each, and they're always a chance. So instead of giving them the arbitrary condition, which wouldn't make sense, we decided to simplify the task by giving them the version where we have familiar metal and wood boxes instead of the gray and yellow boxes. And we also had this sound training here. In this training, we have these boxes that has a hole on top and a ball inside, but the ball doesn't come through the hole. And we would put peanuts in these boxes and pass it to the chimps. And when they shake the boxes to retrieve the peanuts, they would hear the ball hitting the balls and making the clack, 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 or the ding, ding, ding sound. So before each test trial, they received this training. And in the test, they saw exactly the same materials. And we tested again in the causal and the arbitrary condition. And this is what we found: no difference and not different from chance. Only one chimpanzee passed the causal condition, but in the very last session, and there were no chimps in the arbitrary condition who passed the task. We also ran the simplest, the shaken boxes study, but only one individual passed it in the 8th session, meaning after 80 trials, and as a group, they were at chance level again. So to conclude, in this study, we found that by 4 years of age, children were able to make causal inferences based on evidence alone in support of problem solving. We also found that the variation in performance was related to the ability to give a verbal explanation. Those children who referred to the correct way of finding the ball, they also performed better than their peers. On the other hand, we don't find any evidence for 3-year-olds. When the task was simplified, their performance didn't improve. They only could succeed with a causal question. So there is no evidence for disability in 3-year-olds. And same for chimpanzees. But with chimpanzees, we suspect that the task was even more difficult for the kids. So we know that they're sensitive to different sounds, they're capable of matching sounds with objects, and they can infer rewards based on the sound they make. But our task required them to do all of these things at once, and it may have overloaded the chimpanzees' executive functions, and this could have masked their true reasoning abilities again. In addition, auditory cues are transient, so you hear them once, and then at the time of choice, they are not there anymore to guide you. So in our next study, we decided to see if the visual modality would help the animals better. So next, I will move on to the next study where we used indirect cues. But before that, I will take a break and maybe get your questions if you have some. Stop sharing for a second.
Yeah, if you have questions, I have one, but I will keep it.
Okay.
First of all, yeah, you can also type in the chat box. Yeah, Müjde hocam, I see you. No?
Sorry, I couldn't find the raise hand thing. Sorry. It was really nice talk. I love the subject, but I'm a little bit confused. So sorry if I'm not making sense with my question. You are saying you're giving evidence to the inferential account with your PhD thesis, And but it seems like when the interstimulus interval between two stimuluses, when the order of those stimuluses are changed, maybe the association just gets weaker. Maybe it's not just sorry, my son's making me sound. It's not causal, it's a weaker association when the sound happens to be after, you know what I mean? So
I do.
Yeah, I don't know if any reviewer said that, but yeah, that just popped into my head. I have other questions too, but they are more in the realm of social psychology, so I'll wait until the end. Thank you.
Okay. Yeah, I got this question many times as a criticism. So in the causal condition, what they hear is there are these pegs in the middle channel. So they first hear a dig sound and then a ding sound, and then they make a choice. So the sound and the choice is closer in time. In the arbitrary condition, they first hear the ding and then dig, and then they choose. So the distance between the sound and the choice is further apart. And this was could explain whether children did better in the causal condition. But we have another experiment that I didn't include here for the time. But we used the yellow and the gray boxes and we hid a reward in one of them. And then I recorded two sounds where we gave children the dig ding or ding dig. So this is again basically the recorded version of the same conditions, but everything is completely arbitrary. There's no ball falling down or anything. In that case, we gave this to 4 and 5-year-olds, and we found no difference between these conditions. So hearing the sound just before the dig or after the dig didn't seem to make an influence in that case. And yeah, we couldn't find that difference. So I think that was a more robust conclusion for the causal effect we found in the first study.
Great, thank you very much.
Oh, thank you.
I can ask my question maybe. So in your study, there was nothing for 3-year-olds, no causal reasoning, but all of a sudden, after 4 years of age, we see some causal reasoning. So what is the developmental change there other than verbal input? Because also for 3-year-olds, verbal input or verbal scaffolding is seem to be not working. But what is there that influenced the causal reasoning?
Yeah, I'm planning to talk more about this at the end as well. But I think it's the development of language. Children are exposed to more language about how things work in life. And I believe when they are told a lot about unseen causal relationships, they have this representation or they have this new concept of unseen events. And probably this allows them to look for causes even when they have no incomplete information. And I don't want to argue that before 4 years of age, children don't engage in causal reasoning at all. There's even evidence that infants are sensitive to causal relationships. In this case, we were interested in when there is no direct evidence for a causal relationship. They just are given this indirect evidence. Are they interested? Are they motivated to go back and look for these events to explain what has happened? But for instance, in Blickett detector studies, they have direct evidence. As soon as the block contacts the machine, it makes a sound or it doesn't make a sound. In such cases, when there's direct evidence, 3-year-olds are able to solve these problems. Or when there's verbal scaffolding, or when the causal relationships are isolated, for instance, there aren't too many things to think about, and only the 2 blocks are the potential causes, they solve the problems better. But something about hidden causes seems to develop much later, as a protracted development, basically. Does it help answer your question?
No, I am also thinking about the language development, but also the verbal input that the child received. But I don't think that in general, home context in terms of the verbal input from parents, I mean, input with regard to causal reasoning. I'm basically referring this part when I say verbal input is not really studied, right? So I don't think there
are some studies in theory of mind reasoning, which I will talk about at the end, that may show that the home context and what input the parents give while they're reading a book, for instance, to the kids, may make a difference in children's understanding. And theory of mind is also about unseen relationships in a way. There are mental states that you can't see that lead to behavior. So I don't think anything is done on causal reasoning to explore this further. And I know there are more people studying language here. So if you have any comments, explanations, I will be very happy to hear how we can study this further, basically what the causal language does.
Also, we have a comment in the chat box. So Nihal Çiftçi, I think in order to detect which behavior has a role in causality reasoning in chimps, like Honus and Cole study, chimps could expose to the shaking condition instead of the auditory condition. So
do you mean that sorry?
No, just go, yeah. Rather than auditory condition, chimps could be exposed to the shaking condition. So the shaking.
Oh, you mean just shaking the box but not making the sound? Is that what you mean? So in the Daniel Hans and Cole study, they have sorry, I can't see the rest of the messages. Yes, just shaking. They have many experiments in that study. And I think they did actually look at that, whether the shaking or the rotating the cup slowly like this versus this makes a difference. And I think they didn't find a difference in that case. So they don't have a preference for just the shaking motion. But what Povinelli and Pan argues that it has to be the shaking motion plus the sound that they are associating with the location of the reward. And it's hard in that paradigm to come up with exactly the same shaking motion and shaking sound and not be causal. So I think that is the main issue. In some paradigms, you can't distinguish these two things apart from each other.
Yeah. Okay. Any other question? If not, we can move to the second part of the talk.
Okay. Thank you. Okay, so the second study is called the ripped foil, and we use here visual cues, and I worked with my supervisor and Christopher Tarhagin. Sorry, I'm just finding it hard to move to the second slide. Okay. So this study is also a locate the sticker game for children, but instead of sounds, we are giving the participants a visual cue about what happens. So I have a blue and a purple cup, and I cover the tops of the cups with aluminum foil. In the first test phase, I then pick up a sticker lying on the table, and I hide it behind the barrier in one of the cups, leading the foil covering that cup to be ripped. I show the child the end result, and then I put the barrier back again before they make a choice. And this time I pick up a pen and I poke the other cup, leading that foil to be ripped again. Now the child sees that both cups are ripped and they need to ignore the irrelevant cue to locate the sticker in the correct cup. In this case, it's the blue cup. And children in the test phase, they get 8 trials of this. I repeat the sticker, pen, then sticker, pen, sticker, pen. And after they get 8 trials, the order of events are reversed in the transfer phase. So this time I'm ripping the first cup with the pen and then the second cup with the sticker. And in this case, the sticker ends up in the pink cup, for instance. And in transfer phase, they also get 8 trials. So I tested 68 3 to 5-year-old children and 19 capuchin monkeys in this experiment. Our hypothesis in this case was if children inferred the cause of the ripped foil that I was hiding or poking the foil, they should locate the sticker in the correct cup regardless of the order of events. They should succeed in both test and the transfer phase. But if they are using an arbitrary associative rule, such as always choose the first ripped cup because that's what you learned in the test phase, then we expected them to make errors when the order of events is reversed in transfer. Especially the first trial of the transfer phase, when the order of events are reversed for the first time, is critical in terms of determining whether children are making these errors. And here are the results. Remember, this is a within subject design, so all children get the test and then the transfer phase. In the test phase, the overall performance is above chance level. Children are doing well and much better than the Bing machine study. And here is the critical transfer phase. 4 and 5-year-olds are not influenced by the change of events between pen, sticker, sticker, pen, but 3-year-olds' performance drops to chance. By 44 months of age, the older 3-year-olds can solve the problem, but here there's an overlap. So it could be that they may be solving the task initially by association, and then when the test in the transfer phase, the order of events are reversed, they are choosing one of the cups more and leading to errors. And here we see the first trial of the transfer phase. These are the children who got it right, and these are the children who got it wrong. And by 50 months of age, children are performing, before 50 months of age, children are performing randomly when the order of events are reversed for the first time. You can also see the correct and the incorrect explanations. At the end of the task, we asked children again, how did you find the sticker? The correct explanation would be it got popped, you poked them, things like that. And those children who gave the correct explanations performed significantly above chance in the first trial of the transfer phase, only of these, except for these 2 kids here. I tested 19 capuchin monkeys in Edinburgh Zoo with the same setup to see if they could infer the location of the reward. And we found that in the test phase, the capuchin monkeys were above chance overall. In this graph, however, in the x-axis, you don't see age. It is the number of trials in test. So as opposed to children who got only 8 trials, the capuchins could get up to 80 trials if they did not reach the criterion sooner. We did this to make sure that the monkeys were able to use the ripped foil to locate the reward before they reached the critical transfer phase. So we wanted a more robust conclusion. We made sure that they were understanding to use the cues, and then we would see what happened in the transfer. So for comparative purposes with children, I also analyzed their performance in the first 8 trials in test, the number of trials that children received, and we found that at this point, they're not different to chance. In the transfer phase, they are significantly above chance again, but again, if you look at the first trial performance, only 9 out of 19 subjects found the correct location of the sticker. Again, this is not different from chance. So I keep mentioning that the monkeys received more trials compared to children because we wanted to make sure that they could use the visual cue before they moved on to the critical transfer phase that would allow us to distinguish the causal and associative learning. But getting so many trials over and over again obviously brings up a problem. What if they learned an associative rule giving so many trials, such as focus on the state change after the experimenter picks up the reward? If they do not see the ripping event as the effect of the hiding event, but they are only looking for novelty and change, then they would also do equally well in an arbitrary condition. To test this, we ran this control condition where the visual cues are not caused by the food anymore, but they are arbitrarily related to the food's location. So the cups are, in this case, are covered with white paper lids. And when I hide the peanut in one of the cups, I replace the white paper lid with a black zigzag paper lid. And then I poke the other one with the stick, the equivalent of pen. And then I replace the white paper with the black zigzag paper. And in the transfer, the order of events reverse again. So we have this arbitrary condition, and this is the causal condition again, how they performed. And this is what happens. The performance in both test and transfer phase dropped to chance level when we gave them the same associations, but without the ripping real physical events. So to summarize this study, 4-year-olds, but not 3-year-olds, showed evidence of taking an unseen cause into account based on the first trial of their transfer performance. The relationship between verbal report and performance was there again. The children who gave the correct explanations performed significantly above chance in the first trial. There is no evidence for disability in capuchins in the first 8 trials of test or the first trial of transfer, which we focused on for children. But with enough exposure to the situation, the capuchins showed evidence of transferring the solution in a causal, but not in an arbitrary context. To summarize the findings of the 2 studies, these are the 3 questions that were that I was interested in. In the Bing machine, we found the species differences. Children outperformed chimpanzees by 4 years of age. We found an effect of age between 3 to 5 years. 3 to 4-year-olds, they performed differently. We also found this relationship between verbal responses and performance. In the ribbed foil, the species differences is a yes and a no. There are some similarities, but there are major differences. There's again an effect of age and again a relationship between verbal response and performance. So what does it all mean? So is inferring unseen causes based on evidence and early emerging capacity, or is it a late developing ability? Our results from the 2 studies consistently indicate that this may be a late emerging capacity. We found that 3-year-olds may not be asking these why and how questions spontaneously when they are faced with unseen causal relationships. This developmental difference between 3 and 4 years of age also emerged in previous research. It seems the 3-year-olds could detect causality under some constraints. For instance, only when the causal relations were contiguous, isolated, they are fully observable and framed causally. It is possible that in these types of causal relationships, there's not much of an inference making required. It gives a perceptual experience of causation. On the other hand, when the causal relationship is hidden, or when they have to reason about the internal properties of objects that they do not see, or when there is no verbal scaffold, 3-year-olds do not succeed. So what happens between these ages? With the development of language, a novel way of detecting hidden causes becomes available to children. They learn a great many hidden relationships from people around them by being told. So for instance, how emotions lead to behaviors, germs lead to diseases, and electricity makes the toy go. Gell-Mann argues that children are forming this unseen events concept, which acts as a placeholder as children build up their knowledge about the relations in the world. And eventually they generalize this and learn to look for causes even when they cannot directly observe them. But like Hilal also mentioned, the effects of this type of input on children's learning of unseen causes are very difficult to pinpoint, since all children are immersed in cultural input through language. There is some evidence from theory of mind research, which is also about these invisible states. For example, a study with deaf children born to hearing parents showed that they had a marked delay understanding the invisible mental states compared to their peers who were born to families where a parent could sign. This implies that the delayed language access might have a negative impact on children's detection of these unseen mental states later in life. There was an example from a book reading study. If the mother is using mental state words, invisible state words such as think or feel, the children do better in in theory of mind tasks later in the next year, I think, as opposed to children whose parents use more descriptive comments while they're reading the book. It would be very interesting to see if this would also apply to reasoning, causal reasoning about unseen events as well. But to my knowledge, there is no research. And going back to the evolutionary question, is it something we share with non-human primates? Unfortunately, I cannot draw strong conclusions from our studies, our Bing machine study about the abilities of chimpanzees. This was a very challenging task, even for young children, and it required integrating many elements together to solve it, and may have a significant impact on executive functions. On the other hand, the difference we found between the causal and the arbitrary condition in the ribbed foil study suggests that monkeys are not just learning arbitrary associations, they are exploiting the whole information. They understand the causal object-object relationships. But this is not to say that the monkeys were same as 4-year-olds and they were better than 3-year-olds. They were given many more trials and training. The training I didn't talk about in this this presentation yet. They were given this training to learn the task before they moved on to the transfer phase. And research using different paradigms has shown that monkeys and capuchins' performance, the chimpanzees' performance improves over repeated practice, especially if the level of difficulty increases gradually. So it might be that in the absence of a direct visual experience of a causal mechanism, non-human primates may need more experience to fill in the gap. And perhaps this more experience would also help young children, the 3-year-olds, if they had given them 16 trials instead of 8 trials, they could have learned. The problem though, what if the more experience means that they are learning a complex arbitrary rule? There will be people arguing this as well, very reasonably. Our study is, I think, favoring the first explanation, but you never know. And I hate to conclude this way because this is always a given, but I think we just need more paradigms that are non-verbal, that do not task other cognitive functions, and that have robust controls for associative learning to explore this evolutionary origins and also the developmental origins. So I would like to thank you, first of all, for listening to this long talk and everyone who has helped me with my research. I'll stop here.
Yeah, thanks a lot, Zeynep. We have a general question, so I will come back to Nihar's question later. But if there is any specific, questions specific to this research, we would like to hear those questions first. I can start. Test to transfer. Is test to transfer. Yes, I was right. So there is a shift there.
Mm-hmm.
So for the younger kids, it's like perseverance, and even in the dimensional change card sorting task, for the cognitive flexibility, then when there's a shift, they are struggling at first. So
yeah.
Did you have any cognitive flexibility measure in the data?
Yeah, unfortunately, no. And it's probably not coincidental that the development of executive functions is also speeding up between 3 and 4 years of age. So maybe the children's inhibitory control is not developed enough at 3 years to switch to this other order of events. That is a very likely explanation, and we had no way of testing this in the ribbed foil study. But if we go back to the Bing machine, in that case, when we simplified the task to the shaken boxes with metal and wood, we saw that children were actually able to match the sounds, auditory information. I mean, it wasn't loading their executive functions because when you gave the causal question, they were able to solve it now. So for that study, we can exclude the executive functions explanation. But I think you're right with this one. And now that I'm studying more attention shifting, I just notice how difficult it's for 3-year-olds, and we have this problem in this ripped foil study. But the current project I'm working on, we've been collecting data about the development of executive functions, as well as causal reasoning tasks and theory of mind tasks. So we gave children about 16 different tasks. Mm-hmm. So we are at this, we are analyzing the results just now, so I don't have anything useful to say, but I think these types of studies will show whether there's a relationship between executive functions and causal reasoning, like the individual variation is the same within tasks. So that would be very helpful.
Yeah, thanks, Zeynep. All the studies are very exciting and interesting. So
thank you.
Is there any other question for the study too? Mr. Nihal, I will back to your general question. Okay. So, Müjde.
Okay. Again, I'm not sure I'm making sense, but what if the children associated it like this, choose the new rip after the sticker is shown? Like when you see the
like
sticker,
the capuchins.
Yeah, so that wouldn't that give an evidence for the associative account?
It would, if that was the case. And yeah, with the time constraints, I didn't have the chance to do the same arbitrary control for the children. But I think, I think we were pretty confident with the, because of the previous study that we found the same differences by 4 years of age, they're doing well. And the literature also shows that by 4 years of age, children are detecting these relationships quite well. We just trusted what we found, but you're definitely right. This is like with the capuchins, they may have learned an association. It would be something to test.
Thank you very much.
Yes. Now I may move to the general question about the capuchin monkeys.
Yes.
I wonder why capuchin monkeys are better at using tools according to their close relatives. This is just the general questions about the capuchin monkeys.
There are many theories about why cognitive capacities improved in one species than the others among the genera. And I think with the capuchin monkeys, the explanation is the physical challenges of the species where they live, the environmental challenges of finding the food resources cause these species to face like more, if they're faced with more challenging conditions to find food, they develop new methods, for instance, like extractive foraging, like I spoke about. And these may lead the capuchins these may force them to use tools over evolutionary time. And that's the same for the chimpanzees. But there are other explanations these are group living primate species where they have close relationships with other participants in the group, and they have to keep track of who is doing what with one another, who is the friend, who is the enemy. There are subjects who go out of the group to join new groups, so they have to keep track of these social information all the time. And this is another hypothesis that could explain the better cognitive resources, cognitive abilities in social animals. I don't think there's a strict answer that I can give to why capuchins are using tools but not others. But these could be some theories that explain that.
There's a need for one correction about the causal reasoning. So is causal reasoning learning that one event occurs after one another, or is it
Yeah, it's understanding that the events are related to one another. So there is a sequence event, so the cause always has to come before the effect. It's not like in an association, it doesn't matter which one comes first. So there is that temporal relationship, but it's mainly about understanding that the objects or the events are interacting, they're related to one another with a causal link. And I think you could say, not a causal link, but maybe a mechanism that leads one to lead to the other.
I see another question, but it's about another domain. So I'll come to Baran's question. But before, is there any other question about study 1, study 2, müjde?
I was planning to ask after, but I mean, now that you've told, I have a lot of questions, but I don't want to use everyone's time. I think it's fascinating, but so what do you think about this, and what does your supervisor think about all this? So it feels to me that we don't have that much difference with animals. It's just an executive function quantitative difference rather than a qualitative one. But when you say causal relationship, it feels like humans are a little bit better or a little bit different than other animals. And I'm not, I mean, I think I'm more on the, maybe I'm just like randomly talking now, but I'm more on the deterministic side of things, the free, and not believing in free will and all that. And both animals and us, we understand associations, and then we rationalize them with language. The only difference we have with other animals is the rationalization part, and so the causal side comes afterwards. And it's nothing like deep down, there's no difference. It's just a quantitative difference rather than a qualitative one. What do you think about this approach?
Yeah, there are some accounts that argue that this is because we have larger brains compared to other non-human animals, we just have more capacity to information processing, and executive functions are better developed. So these are what explains the differences we find. And if we look at some causal perception studies where there's this Michotian launching, for instance, where a ball contacts another one and collides with it, and it causes this one to move. I mean, I explained it in causal terms, but when you watch this event, you see a causal relationship. Even infants seem to, by looking time studies, they seem to infer causality. But this is the same with newly hatched chicks and also with chimpanzees. These are sensitive, we are sensitive to such information. I think it is not just a difference in terms of our processing capacity. It's not just coming from there, but there are many things that are helping humans to better deal with their environments. For instance, we said obviously the language has a huge impact, but also we are better about metacognition. We know when we don't know things, and we are more motivated to explore them. We have theory of mind, and we understand pedagogical intention. For instance, when in an experimental setting you want something from the child, they know what exactly they have to do, but it requires some training with the animals. Humans have probably better imagination, and they can simulate things in their heads probably better than non-human animals. I mean, we don't have evidence for this. I'm just thinking that may be the case. So these, combined with our cultural accumulation of everything, this would have a ratcheting effect, according to some theorists, that would boost the human's performance in such tasks compared to non-human animals. But then again, in most studies, the human animals were given really arbitrary relationship, and not in the context of foraging tasks, like in our tasks where they were already motivated to get the peanuts or the raisins. In those contexts, they won't have the advantage of the same motivation as human children do. So we need to come up with many different paradigms that look into these relationships and see when everything is ecologically valid, how do they perform when their motivation is really high and the cost of not getting the reward is really high. Would that make a difference? I think these are the things that would make the things comparable between the two groups.
Yeah, thank you. It's so interesting. Like, I look forward to reading more about this afterwards. Thank you. I mean, I have other questions too, but I don't want to. Maybe if we have time, yeah, I can, or I can write her. Thank you.
I'll be very happy. Thank you.
I saw a general comment or question in the chat box. So, have you ever worked on the evolution of laughing?
No, no, I haven't. I know someone, a master's student in St. Andrews, who was working on this, I think, tickling. I think that was what he was working on. But I have no idea what the results are, what he studied in the end. But they engage in, I mean, with chimpanzees, I know from following the sanctuary work, when humans are looking after animals, they tickle them, and they react with laughing, and it's a playful experience, and it seems to improve their adaptation to their new environment. So it has a facilitative role in terms of social engagement. I don't know how you can reach them. I can just ask him. I don't know if it's published, but I'll have a look. I'll contact Hilal about this.
Okay. Okay, so we're about to finish because it's almost 5:20. So if you have any final comments.
By the way, I'm seeing my friends from my master's and I'm really nervous and excited to see them. Just, yeah.
Maybe we should finish now and I will stop recording so we can continue with others.
Sorry, that was a weird remark.